Recording started.
Okay, this is problem 11 in Chapter 8, Section 7, talking about indeterminate forms of L'Hopital's rule. And so we're looking at limits. And the idea here is if we were to apply this limit definition, we would just plug 2 into the equation. If we did that, let's just evaluate the limit just by substitution. We would get 2 squared minus 2 over 2 minus 2. So you get 4 minus 4 is 0, and you get 2 minus 2, which is 0, so that's an indeterminate form. And they're asking you to use L'Hopital's rule, but let's just go ahead and also do it first, doing what we learned in Chapter 1, which was to see if you can factor the polynomial part. And so you would have x minus 2 times x plus 1 divided by x minus 2. And because those are the same, they cancel out as being just 1. And so the original limit becomes just x plus 1. And when we substitute 2 into this expression, we get a determinant form. We get 3. So you get 2 plus 1, which is equal to 3. So that's the answer. Let's prove the same thing using L'Hopital's rule. So L'Hopital's rule says that let's just write it down. The limit as x goes to, let's say, a, which is normally, if it's a quotient, f of, so it'd be f of x divided by g of x. And that's what we have here. This part would be f of x, this would be g of x. But when we do that, and in this case, if we go to 2, we get an indeterminate form. So the other way of evaluating this is to then take the limit of the derivatives. So we get f prime of x divided by g prime of x. So in this case, f of x, we'll just write it out. F of x is x squared minus x minus 2. Therefore, f prime of x, the derivative of this expression with respect to x, is 2x minus 1. And g of x is the denominator. So L'Hopital's rule always has to be applied to rational functions. Okay, so the denominator is x minus 2. So g prime of x, derivative of x is 1, derivative of a constant is 0. And therefore, instead of this original limit, we can rewrite it as limit as x approaches 2 of f prime of x, which is 2x minus 1 divided by 1. And this is not indeterminate. Excuse me. So we just plug the numbers in. 2 times 2 times x, which is 2, minus 1, divided by 1. So we have 4 minus 1, which is 3. So the answer is 3, which is the same answer that we got previously. This is problem 14, section 7. So we look at this, and let's just read it. The limit as x approaches 2 from the negative side of the square root of 4 minus x squared over x minus 2. Now, you look at that and you say, well, does that make, why do they put a minus sign in there? Of course, that's coming from the left-hand side, so it would be from less than 2. And I'm pretty sure it turns out that it doesn't matter whether you come from the positive side or the negative side, you'll get the same limit. So I think they're just using that as an example that you can still apply this approach, whether the limit's to a particular number or coming from either side. And again, if you plug 2 into there, if you plug 2 into the expression, you'll get 4 minus 2 squared divided by 2 minus 2. And you get the square root of 4 minus 4, square root of 0 is 0, so you get 0 over 0. So, again, it's an indeterminate result. And the way we probably would have solved this problem before would have been to use rationalization. So let's just do that as a review. And I'm going to leave the limit sign off for right now while we do the math. So typically what we would do is we would multiply by the square root of 4. Just thinking about this. Actually, I think you could just multiply by 4 minus x squared. It's actually, so it's a little bit different than rationalization. The reason I'm thinking about this, just so you know where I'm coming from, is that if I multiply these two together, I'll get 4 minus x squared times 4 minus x squared, which I can factor into 4x plus 2 and x minus 2, and I can cancel one of those out. So I think that would work. So it's not, like I said, not exactly rationalization, but the numerators multiplied together is 4 minus x squared. The denominator is going to be x minus 2 times the square root of 4 minus x squared. Now I'm trying to think ahead here. If I cancel one of these out, I'm still going to end up with 0 in the denominator, which is not good. So what could I do? The other option would be to have 4 plus x squared. That wouldn't cancel those out. Let's think here. I'm thinking back to chapter 1 when we used rationalization. I'm trying to remember the exact form of the expression. So let me just look back. It's been a while since we've done this, and it's not coming exactly to me. So I just wanted to see what the form was, and maybe okay. So rationalization usually dealt with the square root of something plus a constant or minus a constant. And so we really don't have something that fits rationalization exactly. So I think I'm going to actually we get rid of that. We may not be able to improve on this. We may not be able to do it another way. So we're probably going to have to use L'Hopital's rule. Okay, so it's indeterminate. L'Hopital's rule, again, we have to be dealing with a rational function. So our rational function is 4 minus x squared, which is the numerator, divided by the denominator, which is x minus 2. So if we take the derivatives of each one of these, and then we take the ratio of those derivatives, let us see what we get. So f prime of x is going to be equal to, okay, let's remember what we're doing here. This is 4 minus x squared to the 1/2 power. So we'll get 1/2 times 4 minus x squared to the minus 1/2 power, and then we'll multiply by the derivative of what's inside the parentheses, which is negative 2x. So f prime of x is, these 2's cancel out, so we get negative x divided by the square root of 4 minus x squared. This becomes 1 over the square root of 4 minus x squared. So, okay, and if we do g prime of x, it's just 1. Derivative of x is 1. Derivative of negative 2 is 0. Okay, so now what we're doing is we're going to be looking at this new limit. So we're going to take the limit as x approaches 2 from the negative side. The numerator has become negative x divided by the square root of 4 minus x squared divided by 1. And so the question is, what do we do now? Because we can plug 2 in, and we'll get negative 2 divided by the square root of 4 minus 4, which is 0. So you end up with 0 over, pardon me, you end up with 2 over 0, which would give you infinity. So is that the answer? And this thing is always going to be, okay, that's part of the reason we have the negative thing there, because if we come from the positive side of 2, you actually end up with a square root that has a negative argument. You'd have 4 minus something greater than 4, which would give you a negative sign. So that's why we have the negative sign there from the bottom. And so this is always going to be positive. If this is less than 2, then this fraction, 4 minus something less than 2 squared, is going to be positive. So that's going to be positive. This is going to be positive, and so we end up with positive infinity when we divide by 0, and then we have a negative sign, and so we should get negative infinity as the answer. So this is indeterminate. This, even though it's not really officially defined, it is still, it is determinate. It is determined, and it's determined to be infinity. So I'm just getting the book out here and make sure it did that problem right. So it won't take long here. I'm approaching it quickly. Okay, so yes, you get minus infinity due to the arguments I just pointed out.
Recording started.
Yeah, this is problem 16 from chapter 8, section 7. So again, let's demonstrate that this is indeterminate by just plugging in the numbers. So you get the natural log of 1 squared divided by 1 squared minus 1, and the natural log of 1 is 0, and 1 minus 1 is 0. So there we are. We're indeterminate. Now to find the limit, we can use L'Hopital's rule. So let's go ahead and identify f of x and g of x. And we're going to take the derivative of those two. Now, before we do that, though, let's use the properties of logarithms to simplify this thing. So I'm going to do that in the middle. So the property of logarithms, if you have an exponent inside here, you can just bring that out. Okay, so now we can take the derivative, and so the derivative is going to be 2, which is a constant, times the derivative of the natural log, which is 1 over x. So that gives us 2 over x. And if we do g prime of x, we get 2x. So now, if we then substitute back in, so rather than looking at the limit of the original 2 functions, we're going to look at the limit of the derivative of the 2 functions. So f of x is 2 over x. F prime of x is 2 over x. G prime of x is 2x. And you see these, do those cancel out or not? I mean, we can just plug it in and find out. If you just plug in 2, you get 2 over 1, 2 times 1. So we get 2 over 2, which is 1. So that would be the limit. And I think you can cancel these x's out, so it really doesn't matter what the, just thinking, well, that's not true. I mean, we're just talking about, yeah, I'm just thinking whether, if we put in 0, I can't put in 0, but if you put 2 in here, you get 2 squared, which is 2 times the natural log of 2. You get 4 minus 1, which would be 3. And I'm just thinking, would you get the same number as you got over here if we stuck 2 in instead of 1? And I think this doesn't work for every point. It only works for the points where the function is indeterminate. So this is not like a general statement for the limit, but you can simplify it by taking the derivatives. I think it only applies to when you have an indeterminate form. So anyway, that's something I hadn't thought about, but I think that's true. Now, one thing you can do, and we'll do it for this particular problem, I'm going to make this small. And so there it is. So let's just plot this function. So I'm going to plot, so I'm going to type in the natural log of x squared divided by the quantity x squared minus 1. So we have the natural log of x squared divided by x squared minus 1. And we're looking for the limit as x approaches 1. So let's change the limits here. We'll go from 0 to 2. I don't know what y is going to be, so we'll just plot it and see what happens. Okay, so there we go. So this is the function, and you can see at 1, it doesn't show it on the graph, but it's actually not defined at that point. But you can see that the limit, whether you come from the left-hand side or the right-hand side, is the same thing, and the limit is 1. So a lot of these indeterminate forms, because we have graphing programs now that are fairly easy to use, you can actually plot them and find out the answer to confirm that you got the right answer. I don't think so. And you didn't have to use a simplification here. If you took the derivative of this, you'd still end up with that. It just is a little bit longer if you don't use the properties of logarithms. Okay, this is problem 24, chapter 8, section 7. And this is the first case, first homework problem where we have been going to something other than a finite number. This is going to infinity, and we've actually done these problems before in chapter 3, I think it was, when we were looking at horizontal asymptotes. And what we would have said was that because the order of this term is to the first power, and the order of this term is to the second power, because this is 1 and this is 2, we know that's going to go to, this limit is going to go to 0. So there are rules in Chapter 3, Section 5 that apply to this, but we can also use L'Hopital's rule to simplify it. And again, and we can do this because it's a rational function. So f of x, the numerator, is x minus 1. F prime of x is 1. G of x is the denominator, which is x squared plus 2x plus 3. So G prime of x is 2x plus 2. And so, and in this case, our indeterminate form, what is the indeterminate form? Well, you get infinity in the denominator, numerator, infinity in the denominator. So it's not 0 divided by 0, it's infinity divided by infinity. So how do we get that? Okay, so we take the derivatives. So rather than looking at the original limit as x goes to infinity of this, we have 1 divided by 2x plus 2. And now the numerator does not go to infinity, it just is a 1. So you'd have 1 over infinity, because 2 times infinity is infinity. 1 over infinity is 0, which is the same answer we got by looking at the exponents.
Recording started.
This is problem 34, chapter 8, section 7. So again, this is a case where we're letting the limit go to infinity. If you put the natural log of infinity to the fourth, it's going to be infinity. And of course, the denominator is going to be infinity. So we have this infinity over infinity thing. So we're going to use the properties of logarithms first, and then we're going to apply L'Hopital's rule. So actually, we're going to define what our numerator is. We'll call that f of x. And like we did in the previous problem, we can bring the exponent out to make it simpler. And g of x is the denominator. Okay, so we take the derivatives of each one of these and then look at the ratio of those terms. So the derivative of the natural log of x is 1 over x, so f prime of x is 4 times 1 over x. And g prime of x is going to be equal to 3x squared. So instead of evaluating our original derivative, our original limit, we're just going to evaluate the derivative limit. So we'll have 4 over x divided by 3x squared. I'm going to simplify this by, well, first I'm going to make it a little more complicated by making this into a fraction, and then I can rewrite that as the product of two fractions by taking the reciprocal of that term. So we get 4 over x times 1 over 3x squared. So instead of 3x squared over 1, we get 1 over 3x squared. And so we get the limit as x goes to infinity of 4 over 3x cubed. And so now we can apply the limit. This is going to be 4, of course, and the denominator is going to go to infinity. So we'll end up with a constant over infinity, and that goes to 0. And that's because this gets larger more quickly than that gets larger. And so if we plot that, let's go ahead and let's open up the graphing program and plot this particular function. So we get the natural log of x to the 4th divided by x cubed. And the limits, I'm going to increase the limits. We'll start with 0, but we'll go up to 10 just so we can get some distance. And if we graph it, you can see that as we go out to infinity, that we do approach 0 as far as the function is concerned. So that's it. And
recording started.
Okay, this is problem 37, chapter 8, section 7. Okay, what do we have here? Well, we're going to have infinity times infinity, which should be infinity. So it's not. I was just thinking about that. Is infinity times infinity an indeterminate form or not? So I'm just looking back at in the book. They actually discuss such things. We've got infinity divided by infinity, 0 divided by 0, 0 times infinity, 1 to the infinity power, infinity minus infinity, 0 to the 0. Yeah, so I don't really actually see this as an indeterminate form. You just get infinity. So I'm just going to look it up in the book here because I don't even think we have to do anything. So this is 37. Yep. Okay. So we don't. This is not even an indeterminate form because you just have infinity times infinity, and that's just equal to infinity. So the answer is infinity.
Recording started.
Okay, problem 37 is our first example of where we don't have initially a quotient, but we can create a quotient. And when we have a quotient, then we can use L'Hopital's rule. So the first thing that we would do is we would rewrite this as x cubed, and we change cotangent into 1 over the tangent. So now we have x cubed over the tangent of x. So now we have, so now we can apply L'Hopital's rule. Okay, let's see, is there anything I need to tell you about that? Okay, so let's take the derivative. Well, let's actually define the functions first. F of x is the numerator, g of x is the denominator. So what is the derivative of f of x? It's 3x squared. The derivative of the denominator is secant squared of x. Okay, so now we create our new limit. Let's go ahead and just add another page here. So our original limit becomes the limit as x approaches 0 from the positive side of, we have 3x squared divided by the secant squared of x. And so if we let the numerator x equals 0 in the numerator, what we will get is we will get 0. And the secant of 0 is the same as 1 over the cosine of 0. The cosine of 0 is 1. So 1 over the secant is 1, and you square that and you get 1. So the answer is 1 for the denominator, and so we get 0 as the answer. And let's just plot these functions separately and then look at them as far as the final answer is concerned. So let me get the graphing program up. Actually, I gotta stop sharing this. Okay, so here we are. And I'm going to plot x cubed. Is that right? This is problem 38. Okay, x cubed, the cotangent of x. And let's just plot those two to start with. And I'm going to go from x equals, since we're going to x equals 0, let's go from -1 to +1. And let's see what it looks like. So this is x cubed. And this is the is that the cotangent or tangent? That's the cotangent. Okay, so I was right. So you can see the cotangent goes to 0. So you're going to have, cotangent goes to infinity as x approaches 0. So this is the cotangent approaching from 0 from the plus side. So this goes to infinity. This goes to 0. So you're multiplying 0 times infinity, which is indeterminate. So then you have to use L'Hopital's rule to take the derivatives. So if we plot the actual combination of these two functions, which is going to be x cubed times the cotangent of x, you can see that the product of these two, the product of x cubed and the cotangent of x is the green line, and you can see how it approaches 0. It's undefined at 0, but it approaches 0. These are both negative, so the product is positive. And what's happening is that x cubed gets smaller more quickly than the cotangent gets bigger. And so we end up going to 0. If it was otherwise, if this went to infinity more quickly than this went to, the red curve went to 0, then we'd probably go to infinity instead of 0. So that's how that works. So I'm going to stop sharing this, start sharing my smartboard. Okay, so that's how that works. Let's repeat what we did. We took this product, and in this case, if we went to 0, we'd have 0 cubed, which is 0, times the cotangent of 0, which is infinity. So you'd have 0 times infinity, and that's another indeterminate form. Now, if you rewrote it as this, what happens is you get 0 divided by 0, which is another indeterminate form. So they're both indeterminate, and they're equivalent to each other.
Recording started.
Okay, this is problem number 40, Chapter 8, Section 7. So let's just check and make sure what kind of indeterminate form we have. And I'm just looking at this. As x goes to infinity, we'll have x, which will be infinity, and you'll have the tangent of 1 over infinity, which is 0. And the tangent of 0 is 0. So we get infinity times 0. So that is one of these indeterminate forms. It is not a rational function at this particular point. So we have to rewrite it as a rational function, and then we can take the derivative. So let's we can either take the tangent to the bottom and make it the cotangent, or we can rewrite x as 1 over x. So I'm going to choose that way. And so now we take the derivatives of each one of these, but as usual, I keep forgetting here. Let's just write them out. So the derivative of the tangent of 1 over x. Okay, so this you have to use the chain rule, and what we'll end up with is the derivative of the tangent is the secant squared. And then you multiply by the derivative of what's inside, which is going to be negative 1 over x squared. So that's because this is 1 over x is x to the minus 1 power. When you take the derivative, you'll take the exponent, which is negative 1. That's where the negative sign comes from. You'll subtract 1 from the exponent, so it'll become negative, instead of negative 1, it'll become negative 2, which is the same as 1 over x squared. Okay, now we have g prime of x, and we just did that, so we know what it is. It's negative 1 over x squared. So now we look at that limit. So we're going to, instead of looking at that limit, we're going to look at secant squared of 1 over x times negative 1 over x squared divided by negative 1 over x squared. And you see these two cancel out. So what we're looking at is the secant squared of 1 over x. 1 over infinity is 0. Secant of 0 is 1. So 1 squared is 1. So what we end up with is, the secant of 1 is the same as 1 over the cosine of, pardon me, the secant of 0. Let's start over again. The argument is 1 over infinity, which is 0. So let's write that down. So these cancel out, and we have the secant squared of 0. That's the same as 1 over the cosine squared of 0. The cosine of 0 is 1, so we get 1 over 1 squared, which is 1. So that's the limit. And let's just see if that really is true by plotting it. So we're going to close this, and we'll open up the graphing program. Okay, that's left over from a previous problem, but we're talking about x times tangent 1 over x. And we're wanting the limit as x goes to infinity, so let's put 0 in for the minimum and put 10 in. 10 is not infinity, but it'll at least give us an idea of what's going on. And so there you go. So here, as x approaches infinity, you can see that the function approaches 1, which is what our answer was. So let's just go back and review what we did. So first thing we did is we evaluated the original limit, found out it was indeterminate, infinity times 0. We created a rational function by rewriting x as 1 over x. We then used L'Hopital's rule, so we took the derivative of the numerator and the derivative of the denominator. We took that ratio. We were able to cancel out these two terms, and all we had left was the secant squared of 1 over x. 1 over x as x goes to infinity is 0, so we get secant squared of 0. Secant squared is 1 over cosine squared, so we have cosine of 0, which is, cosine of 0 is 1, so we have 1 over 1 squared, and we got 1.
Recording started.
Okay, this is problem 45, which is different than all the other homework problems. And basically, what we get is if we let x go to 0, we get 1 to the infinity power, which is a form, is an indeterminate form, 1 to the infinite power. So how do we handle this? Because you can't create a fraction out of this. So we use the properties of logarithms to simplify things. So let's let y equal this limit. Y is the limit as x goes to 0 from the positive side of what? Oh, we just write it down. So it's 1 plus x to to the 1 over x. Now, so we use the properties of logarithms, so we take the logarithm of both sides. So you'd have the logarithm of the limit as x goes to 0 from the positive side of 1 plus x to the 1 over x. And you can move the logarithm part inside the limit, so it becomes the limit as x goes to 0 from the plus side of the natural log of 1 plus x to the 1 over x. And I think that's why we have the plus sign here, because if I had a minus sign, then I think we would have a problem. Is that true or not? No, I was thinking because if it was a 0 logarithm, but it doesn't end up being 0, so I really don't think it makes any difference, but we'll look at that later. Okay, so what we do is we add another page first, and then we use the properties of logarithms to change this into something that is a ratio, is a rational function. So we have the limit as x goes to 0 plus of 1 over x times the natural log of 1 plus x. So the exponent, which is 1 over x, comes out. And now we have a rational function. We have the natural log of 1 plus x over x. If you let x go to 0, you'll get 0 in the denominator, and you get the natural log of 1, which is 0, so you get 0 over 0. So it is an indeterminate form in its current format. So what we would do is we would define the numerator as is going to be the natural log of 1 plus x, and the denominator is just x. So that's our denominator, that's the numerator. And so f prime of x is going to be just 1 over 1 plus x, and g prime of x is just 1. So now we can plug it in, find that limit. So what we're doing is we're looking for the limit as x approaches 0 from the positive side of, instead of this, we're going to do that, which is going to be 1 over 1 plus x divided by 1, which is the same as, well, we just plug it in now. So if we plug in 0, you see we get 1. Okay, it's because you get 1 plus 0 is 1, 1 divided by 1 is 1. So we know that the natural log of y, which is our limit, is 1. And then so if you take e, raise e to both sides, this becomes just y, and this becomes e. And so the limit of this original expression should equal e, which actually is, I think you could say the same thing about if x goes to infinity, but I'm not sure about that. Actually, no, it's because this has to do with like interest rate. And if you let the interest rate go smaller, but you let the number of periods go to infinity, then you end up with e. That's the whole idea behind that. So we're going to look at the graph of this function. So let's put that up. So this is problem 45, and so if we do 1 plus x to the 1 over x power, is that right? Is that what we're doing? Yes, okay, so we graph that, and let's go from negative 2 to positive 2. And so we see a curve like this, and that actually kind of goes a little wacko right here at 0. But if we zoom in, it doesn't show that kind of weirdness to it. If I go back here, you can see I've got this. And I think that's just some graphing anomaly. But if I zoom in on this point, you can see that at x equals 0, I get 2.7. If I went exact numbers, we would get exactly e. So that does prove that, again, the function does not exist at 0, but the limit does exist.